Tell me your name.
Joseph Fournier.
Okay. And what's your research, Joseph?
Well, I'm in physical chemistry, microwave spectroscopy. And microwave spectroscopy measures rotational energy levels of molecules. And since rotation depends on the moments of inertia, the moments of inertia in turn depend on the location of the atoms, the various conformations of a single compound give unique microwave spectra, therefore can be distinguished by microwave spectroscopy. Now, in recent years, we've been studying substituted acetylene compounds, and the reason we got into that was because of the ethane rotational barrier. Now, ethane and other simple hydrocarbons are known to exhibit staggered structures rather than eclipse states. In ethane, the energy difference between the two is about 3,000 calories per mole. Now, the controversy was over why the staggered form is favored. The traditional explanation is that in the eclipse form, the hydrogen atoms are essentially too close to each other and have strong repulsions, and that's alleviated in the staggered conformation. The second explanation is that of hyperconjugation, where the staggered form is stabilized by the overlap of bonding orbitals with antibonding orbitals. There's been a lot of back and forth between the two camps in theoretical studies. Being experimentalists, of course, we want to try to probe this spectroscopically. So we did a clever experiment on the butane analog 3-hexyne, which is butane separated, you get two ethylene groups separated by a C triple bond C spacer. And so if the main interaction here, or steric interaction, we expect to see an eclipse structure, sort of like this, the ethylene groups lined up. Because at longer distances, steric interactions change from strongly repulsive to weakly attractive. If, on the other hand, hyperconjugation were the main interaction, we would expect to see a staggered form, so that's the only way for these bonding and antibonding orbitals to correctly align. And in fact, our microwave spectroscopic study showed the structure of 3-hexyne to be eclipsed, so consistent with the weak dispersion attraction. So to continue this work, we looked at even longer extended butane analog 3-hexyne, which is this molecule here. So an additional C triple bond C spacer. So we want to see if this weak attraction was still dominant this longer distance, and just how small this rotational barrier is. So first we did our quantum mechanical calculations, which show the energy difference between the staggered and eclipse form to only be about 3 calories per mole, so much smaller than the 3,000 calorie per mole ethane barrier. So these numbers are so small, are they even reliable? Can we trust them? Well, to test that, we looked at the well-established butane barrier. Again, butane has an ethane-like barrier with two stable minima, a completely staggered form, which is the lowest in energy, and also a gauche form at plus or minus 60 degrees. Net energy difference is known experimentally to be 660 plus or minus 22 calories per mole. So we did the same calculations for these two forms of butane that we did with the 3,5-octadiene, and we get an energy difference of 686. So it's at least 4 calories per mole off from the experimental value. And again, with the octadiene, the energy difference is only 3 calories per mole. So this tells us that this energy difference is insignificant, so it implies a zero rotational barrier. So we can't rely on calculations, we must again rely on our experiments. So we use a pulse jet Fourier transform microwave spectrometer. So essentially our sample enters the chamber from room pressure to near vacuum as a puff of gas, and because it's going from room pressure to near vacuum, the sample becomes cooled down to about 2 to 3 Kelvin, so just above absolute zero. So this locks the molecules into their lowest energy minima. We then emit pulses of microwave radiation. There's a rotational transition at that frequency. It will emit that radiation, and then it will re-emit it when it falls back to the ground state, and we'll detect that emission. So what did we expect? Well, a C2H staggered structure has no net dipole, and so it won't react with this microwave radiation. It won't give a microwave spectrum. What's called a C2 structure, which would be anywhere between 0 and 180, has two equal minima, plus or minus whatever that angle is. And because the barrier is so small, we would expect to see what's known as tunneling between the two minima, and this would cause our transitions to become split. C2V eclipse structure just has one dipole moment along the B axis, it should give a simple spectrum. And that simple spectrum is shown here on the top. So we have one family of lines here, lying closer together, and then the second family is spaced apart. And the spacings are about 1,000 megahertz. Those spacings become smaller with each transition. So what did we observe? Well, we first searched for this, what's called a Q-branch family. We didn't find it. We then turned our attention to this second family, and we found a bunch of lines going all the way up to about 15,000 megahertz. But we didn't find anything past that. And these spacings are a lot closer to what's predicted for the C2V form. So we were able to assign these lines to these transitions, this is the lower state to the upper state, and they give B and C rotational constants that are nearly equal, consistent with this symmetric spacing. However, the A constant is only 6,000 megahertz. And this is puzzling because that A constant is predicted to be somewhere between 8,000 in the eclipse form or 13,000 in the C2H staggered form. So it should be somewhere in this range, and it's not, and that's puzzling. So this spectrum, in any case, is not consistent with the C2H form because we have an observable spectrum. We don't observe tunneling splitting, so it's not consistent with the C2 structure, and it's also inconsistent with the staggered form. So that only leaves free rotation of the N groups. And free rotation is consistent with the equal spacings. However, the small A constant is still puzzling, and we're still trying to figure out what's going on and why it's so small. But in any case, we know that it's not eclipse C2V, so we can conclude that these dispersion attractions are too weak at this longer distance. So it's really good work. We don't believe a free rotor like this has ever been studied. Symmetric rotors like a methyl group have been studied, and we know how to handle that. But an ethyl group is asymmetric, and we're not sure exactly how to handle that, and it hasn't been done yet. So it's really fascinating, really great work.
Great. What has the private support meant to your research and your ability to do the research?
Well, it's a summer grant, so it allowed me to go over the summer. We actually do our experiments at Wesleyan. We got a joint grant with them and decided to build a spectrometer there. So it allowed me to go there, almost every day over the summer to get this work done. It was really hard at the start. We were looking for these lines, and it looks like they're close together on here, but in reality, they're really far apart. So it took a lot of time until we finally found some lines, and actually worked one over into the fall. So that, and also I came up here over the summer to do all this computational work. So it really helped out in being able to get the work done and complete it.
Great.